people still joining the meeting. Welcome to our first webinar for our Better Water for All Network Plus. I'm Professor Bingu at the University of Surrey, project lead of the Better Water for All Network. So this is our first webinar, and I will introduce our network briefly to start the webinar, followed by Dr. Yan Zhang from Westlake University to give us a talk on the forever chemicals. It's not forever, PFAS in water. I think, let's wait for 1 more minute to let more people join. But before that, I can also introduce some housekeeping rules. You can see there's a Q&A button on the Teams tabs. So if you have any questions, please use the Q&A and type your question there. So at the end of the talk, I will pick up questions from the Q&A panel. And you are joining automatically unmute, and please keep muted. If we find that there is a need to unmute you and you let you speak, we'll do so. But please use the Q&A panel as the mainstream for asking questions. Okay, so I will start introducing our network. So our network is EPSRC Turk Better Water for All Network. And there are 6 networks funded by EPSRC Turk scheme, sharing 10 million pounds for 3 years. And each of our network focuses on different themes. And here we are focusing on the water. And why water? Just give you some example of what water resource we use and we live with. In England, the water quality is not very good. There are some numbers showing that even in this developed country, our surface water experience some issues with chemical and biological quality, and the news keeps coming up with contamination, with chemical cocktail contamination, and with water resource problem. And it's not just a UK problem, it's a global issue with around the globe. There are water scarcity and water safety, water quality issues. And in the future, with climate change, all these issues will only getting more serious than getting lessened. What if we look into the future? What solutions do we want to have? So with opinions from stakeholders, from academic and industry, we think that water reuse and the circular economy would be 2 key solutions for future. And these concepts are not new. Water reuse, circular economy, why they are not applied to the water sector? There are lots of barriers, or there are a lot of issues to apply these concepts into the water sector. We cannot ignore the contaminants and the risks from the water when we do water reuse and circular economy. And chemical and biological micropollutants are some of the key issues that are raising the risks. So if we look at safe and clean water for water reuse and circular economy, we face a paradox. We want the water to be safe, we want the public to be satisfied, but then we can face high cost to purify the water. So there is this paradox, and our network, we want to re-engineer the water engineering to safeguard equitable and resilient access to high quality water for future generations, not only by the technological innovation, but also by collaboration, co-creation solutions with systems approaches. so we can achieve efficient, low cost, and sustainable technologies. The network, we have a cross-discipline network, and we co-create roadmaps with flexible funding to support actions and innovations. And we also do water and engineering advocacy for the public. These are the project partners of our network. And the project team, we are from University of Surrey, Newcastle University, Harvard, and Cranfield University. These are the project team leads and two lovely network managers that you see on the screen, Miriam and Zhufang. So if you have any question about the network, you want to join us, you want to present something, or if you want to get support from the network, you can contact Miriam and Zhufang. So for the network activities, we do engagement, we support networking and co-creation with industry, policy, and public. We also support early career researchers and early career engineers, and we have flexible funding to spark innovation. This includes annual network events, seminars, webinar working group, outreach, strategic workshops, co-design of research, and we will have open calls for cross-team workshops. For early career, we have placement, second month, training, conference, travel, and for flexible funding, we will have every year one call for flexible funding projects, small study, single discipline, and cross-discipline, and we will ensure double-blind review for fairness and excellence. So in February, the EPSSC launched the 6 networks, and our water network officially launched 3rd of October with in-person activity, and we have our website launched this in October, so you can scan this QR code to browse our website. All the funding information, the technical themes, all the information is there in the website. We will have calls for working groups and flexible funding calls, so keep in touch so you can receive updates from our network. And in next year, we'll have workshop series and annual conference. So to be posted, do join our network for free membership, and you will receive activities and funding calls from us. With that, I will now introduce our speaker, Dr. Yan Zhang from Westlake University in China. She is the lead of the analysis and the degradation mechanism of emerging contaminants lab at Westlake University, and her research employs advanced mass spectrometry and quantum chemistry approaches to tackle the fundamental mechanisms of PFAS and develop innovation and the environmental occurrence and fate of hidden PFAS. So please join me to welcome Yan Zhang for her talk. Yan, we can see your screen now. Yes.
Okay, thank you so much. I think my voice is also clear. Okay, so good afternoon, everybody. So the presentation I'm going to share is our latest work on structure-dependent defluorination mechanism of PFAS by advanced oxidation reduction process. So I'm an assistant professor in Westlake University. So I will start with a brief introduction of myself, and then we will move on to the topic of today. So I'm educated in China, and then I stayed in US for 1 year as a visiting student. And then I did my postdoc at McGill University in Canada. And then in 2021, I moved back to China to join a newly founded university called Westlake University and start my independent career as assistant professor. So like being said, our lab is called Analysis and Degradation of Emerging Contaminants Lab. And you will soon know our major work in the past 5 years. So let's start with a brief introduction on what is PFAS. So PFAS is short for per and polyfluoroalkyl substances. If you can see my mouse, so here are two examples of the most extensive detected PFAS. One of them is PFOA, one of them is PFOS. So you can see they are structured chemicals with many carbon-fluorine bonds in their structure. And these chemicals are widely used in firefighting foams, pharmaceuticals, fluorochemical industries, and it's also used in to produce the PTFE that is widely used in our cooking oil as a non-sticky pans. So because of their widely usage, and they are highly detected in the general environment. And not just about this traditional structures, PFOA and PFOS, because they are a lot of functionalities. So to serve their functionalities, we have developed a lot of structures like these new structures. So what am I trying to say is that PFAS are widely used, and they are also, as a contaminants, they are also widely detected in the global environment. And here is a map in, I believe this is a PFAS occurrence in the groundwater globally. So over here, I just want to explain why PFAS are widely used, because the thermal and chemical stability of the carbon-fluorine bonds, they are one of the most stable chemical bonds. So because of their stability and their thermochemical stability, and they're both hydrophobic and lipophilic, so they have a lot of enhanced properties. Like they are very good surfactants, and they resist the water and resist oil. And when they use in pharmaceuticals, they also have very high bioactivity, selectivity, and membrane permeability. So because of these enhanced properties, they are widely used in a lot of consumer products, high-tech industries, and pharmaceuticals. And also, because of their stabilities, once they are released in the environment as a contaminants, they are also very persistent in the general environment. And also because their large molecular weight, they are also bioaccumulative, and they can induce a lot of toxic effects and antibiotic resistance. So PFAS are a very serious or headache contaminant. But the thing with PFAS is that they are also essential chemicals. So on one side, we have to use their functionality, and on the other side, we have to deal with its adverse effect. So it means that if we can restrict a certain structure of PFAS, for example, PFOA and PFOS, they are restricted in a lot of area, in a lot of countries, but their functionality cannot be replaced by other chemicals. So generally, there are two strategies to overcome these obstacles. One is to use structural similar chemicals, that is called substitutes or replacements, to keep their functionality. Another is to move the factory that produce PFAS to like more developing countries. So I'm saying this is because like in North America, people start to restrict PFAS since 2000. But for example, in China, we start to produce a lot of PFAS since the year 2000. And our contamination becomes very serious since 2000. So I think over here, I'm trying to say is that we're going to face the contamination and remediation issues of PFAS in the long run. So, so these two chemicals, PFOA, PFOS, as I mentioned earlier, is two chemicals that has been included in the standards for drinking water quality in China as reference levels. So they are not strictly restricted, but referenced. And also these 5 structures are included in the enforceable limit in drinking water by US EPA. So these are the regulated PFAS in drinking water. This is in China as reference standards, and this is in US as enforceable limit. But over here, I want to emphasize that what we are going to deal with on PFAS is not just about these structures. So for example, over here, so this is our recent study, which hasn't been published yet. So we collect the water from every province in China, and we analyze 82 PFAS in this tap water samples, and we found that 64 out of 82 PFAS in 12 classes were detected, and 100 every samples have detected PFAS, especially the novel ones. So here are the structures of PFAS we have detected, and each color represents different individual PFAS or PFAS classes. So here is the concentration. So I didn't I didn't expose the places because a little bit sensitive, but we can see over here that the concentration of PFAS in certain tap water are very high. So the tap water and the raw water is where the tap water produced. So we can see that the PFAS concentrations in these raw water samples and tap water samples are very similar. So in the river B, the concentration can reach over 3,000 nanograms per liter. And it is much better in Lake C, but the concentration is still about like 15 nanograms per liter. And here is the composition of PFAS. So this is the concentration and this is the composition. Different color represent different PFAS classes. So this shows that from the raw water to tap water, so we will have drinking water treatments. But we can see that the concentration does not change, the composition does not change. So it means that the drinking water treatment plants does not work on PFAS at all. So any PFAS occurred in the source water will eventually end up in our tap water. So you may ask, so what do we do to protect us if the drinking water plant does not work? So if we really want to protect us, a quick way is to use household purifiers. For example, this is also from our data, and we can see that if we analyze the concentration of PFAS in the tap water and in the purified water after the RO purifiers, so the green one is the purified water and the purple one is the raw tap water. We can, and the dashed line over here is the China's reference standard, and this one is a US reference standard. We can see for P4A after the purifiers, especially for the RO technology, the concentration of P4A is highly reduced. And before the purification, the tap water has the concentration of P4A in the tap water has mostly exceed the reference standards in China and the US enforceable limit. But after the purification, now okay, we are good. So if our tap water got contaminated, we can really use household purifiers to eliminate the PFAS in the tap water to protect ourselves. But this does not solve the problem. The PFAS from the PFAS in the tap water coming from originally coming from industry wastewater, and there are multiple PFAS structures occurred in this industry wastewater, and the drinking water treatment plants does not work on PFAS, and also the wastewater treatment plants does not work on PFAS. So any PFAS that appears in the industry wastewater, once they discharge into the surface water, and if we use the surface water as our drinking water source, our tap water will be contaminated. So the most effective way to solve the contamination of PFAS is to destroy the PFAS as an emission source. So in this way, that means that we destroy the PFAS before the industrial wastewater was discharged. And this way we can eliminate downstream PFAS contamination and protect our drinking water safety. So the key question over here is that how do we destroy the PFAS, especially we have so many different structural PFAS in the industry wastewater. So Before I move on, I just want to emphasize that by destroy or degradation of PFAS, what we mean is that we break the carbon-fluorine bonds, the organic carbon-fluorine bonds into fluoride ion. So when we break the bonds, the carbon will be released. Sometimes will be released as carbon dioxide, and the organic fluorine will become inorganic fluoride ion. So fluoride ion is also a contaminant, but its treatment technology is very mature. But how to break organic carbon-fluorine bonds into fluoride ion is the issue, because as we mentioned earlier, the carbon-fluorine bonds are very stable. It's the most stable bonds in chemistry. So, and another thing is that what we remember is that we have so many carbon-fluorine bonds in the structure. So what we really want to achieve is a complete defluorination. That is to break all the carbon-fluorine bonds, all the organic carbon-fluorine bonds in the structure into and release them as fluoride ion. So please remember, our goal is complete defluorination. And of course, we want to understand the mechanism and how this reaction occurs and the structure dependence. So in this way, we can improve the efficiency for the technology we are going to apply. So after explaining our objective, how to is to degrade the PFAS to target complete defluorination, let's go back to see the structure of PFAS. So in the global market, there are like 14,000 PFAS. And here is just some examples of the PFAS structures. And they are, you may think that they are very complex. But if we look closely, we can see that the complex PFAS structures in the left is actually a combination of the different functional moieties in the right. So we divided these functional moieties into 4 groups. Perfluorocarbon chain, a polar head groups, a spacer group, and inserted heteroatoms on the perfluorocarbon chain. So if we look closely, we find that these structures in the left are actually combinations of these 4 functional moieties. And then you may also notice that some of the functional moieties are colored and some of them are not. So the colored functional moieties is the one that we identify them as oxidizable sites. So over here, like what I'm trying to say is that we have so many PFAS structures in the global market. And when we do degradation, we cannot go one by one. We cannot run experiments for every PFAS structures. So what we do is that we extract the key functional groups and divide them into different groups. And then what we really want to unravel is to see how different functional moieties determine the defluorination mechanism. So in this way, we can understand, we can know like how to treat the diverse structures of PFAS when we run them in run into them in the industry wastewater. Okay, so what I'm going to start with is this structure. It's called 6,2-FTSA, and we can see their structures. It contain a perfluorocarbon chain, a sulfonic head group, and 2 carbon hydrogen moieties. And then the technology I'm going to use is a hydroxy radical-based advanced oxidation process. So why hydroxy radical? Because like in a lot of water treatment, we use advanced oxidation for water treatment. And during this advanced oxidation process, hydroxy radical is a key oxidant, and it is a very powerful oxidant. And it can degrade a lot of contaminants, non-PFAS contaminants. But when it comes to PFAS, it can only work on the carbon-hydrogen bond over here. It cannot work on carbon-fluorine bond or the sulfonic group over here. So when hydroxy radical work on carbon-hydrogen bond, it will convert them into carboxylic group over here. So this structure will become a perfluorocarboxylic group, perfluorocarboxylic structure over here. And then this structure does not react with hydroxy radical anymore. And if we really want to degrade this structure, we have to use another oxidative radical. It's called sulfate radical. And this sulfate radical can be generated from a precursor oxidant that is called peroxydisulfate. And after heating or UV irradiation, we can produce sulfate radical. And then in our study, we found that sulfate radical directly cannot work on the structure either. So it has to be under low pH, and the sulfate radical will be converted into protonated sulfate radical. And then this protonated sulfate radical can attack the carboxylic group over here, and then it can induce defluorination reactions. So, and then they can convert all the carbon-fluorine bonds into fluoride and all the carbon into CO2. And then in this process, we can achieve complete defluorination and complete mineralization. So mineralization means that organic carbon become carbon dioxide. Defluorination means that organic carbon-fluorine bonds become fluoride ion. And then you may wonder how this process happens, how hydroxy radical convert carbon hydrogen into carboxyl group, and how protonated sulfate radical attack this carboxyl group and then induce the defluorination. So over here, this is detailed reaction pathways, and we have published these papers quite a few years ago to describe how step-by-step this reaction happens. So this is a hydroxy radical induced carboxylation pathway, and this is a protonated sulfate radical induced defluorination pathway. So I'm not going to go details over here, and if you're interested, you can read our papers. Over here, just want to emphasize hydroxy radical can convert this carbon-hydrogen bond into carboxylic group, and then protonated sulfate radical will attack this group and induce defluorination reactions. We can see over here the perfluorocarbon chain was shortened after these reactions. So then that is one example of the oxidizable side that is with carbon-hydrogen bond. And this mechanism also works for other oxidizable moiety, like the double bonds, the amide and the sulfonamide derivatives. And the hydroxy radical will convert all this oxidizable side to carboxylic group, and then protonated sulfate radical will work on them and then induce defluorination and mineralization reactions. And in this process, complete defluorination will be achieved, and then we testify this reaction by 26 PFAS structures. And here is the 26 PFAS structures. We can see, so these structures contain the carboxylic group, and this structure contains a carbon-hydrogen bond. This one contains a double bond, and this is an amide or sulfonamide. We can see that they all achieve 100% defluorination. And over here, this is the kinetics. For example, this is the kinetics of this structure. And this is the degradation of the parent compound, and this is the generation of fluoride ion. And these are the intermediates. They are all shorter chain of dispersion. And then for this structure that contains two carboxyl groups, they also form shorter chain versions of this one. And for this structure, they contain a carbon-chlorine bond in the end, and the intermediates is also the shorter chain version of this one. But remember that they all achieve complete defluorination. And for the structures like this, the intermediates are also shorter chain of perfluorocarboxylate. We call them PFCA. And also for these structures, they also generate the carboxyl structures. And this is the detailed reaction pathways. So why I'm emphasizing the oxidizable moieties? The reason is because, like in contaminated environments, so this is from the non-toxic analysis of PFAS in contaminated environments, and this is the number of PFAS identified, and this is the number of PFAS that contain these oxidizable moieties. And then we can see that over 90% of the PFAS detected in the contaminated in the environments can contain these oxidizable sites. So it means that by using the oxidation technology, we can treat over 90% of the PFAS, and we can then they can achieve complete defluorination in oxidation technology. And then you may ask that, what if the structure does not contain an oxidizable site? For example, over here. So the structures like PFAS, it does not contain any oxidizable site. And also this chloride PFAS does not contain oxidable sites. So for these structures, we cannot use oxidation to degrade them, but we can use reduction method. So the reduction method we use in our study is a hydrate electron-based advanced reduction process. And this hydrate electron was generated from UV irradiation of sulfate. And once the hydrate electron was generated, it can attack the carbon-fluorine bonds directly and then generate an unstable intermediate. And this unstable intermediates will cause defluorination. And then eventually the carbon-fluorine bonds will become carbon-hydrogen. In this way, the organic fluoride is released as fluoride ion. And then the key questions we want to answer over here is that, can this process achieve complete defluorination? And then what is the structure-dependent defluorin mechanism? And then we want to know if there is a theoretical framework that can allow us to predict the structure-dependent reactivity. So for this study, we have investigated 41 PFAS. And this is the 41 PFAS we have investigated. And we found that 34 of them can achieve 100% defluorination. So the x-axis over here is defluorination. We can see most of them can achieve complete defluorination. But for the structures like this, the shorter chain versions of these structures, like over here, some of them even don't react, and some of them cannot achieve 100% defluorination. And the question over here is that how different functional moieties affect the defluorination. But before we answer this question, we also let's look at the reactivity of different structures. So the x-axis over here is the logarithm of the degradation rate constant, and it's in logarithm. So it means that the rate constant or the reactivity of PFAS in the hydrate electron system is highly structure dependent, and it spans 4 orders of magnitude. And also we can see that for different PFAS classes, they have different chain length dependence. For example, the orange one over here is a PFAS that contain carboxylic group, and they have different chain lengths. And then we can see that they don't show chain length dependence. It means that no matter how long the perfluorocarbon chain, their reactivity is very similar. But for the structure like this, so the structure is this PFSA, and we found that the longer the perfluorocarbon chain, the higher the reactivity. So the key question over here is that why distant classes of PFAS differ in their chain length dependence? And the key questions we want to answer is the defluorination mechanism. Like, what is a mechanism that determines the structure-dependent reactivity? So, here is the kinetics of different chain lengths of PFCA, and here is the kinetics of different chain lengths of PFSA. So, to answer the questions, let's closely look at the how hydrate electron degrade PFAS. So after UV irradiation, hydrate electron was generated, and then this hydrate electron will undergo electron transfer process and form a unstable intermediates, and these intermediates will cause defluorination. So we call this step defluorination step. And actually, the studies before us has investigated the defluorination step. So by investigation, we mean to calculate the free energy of activation for this step. So in chemistry, we know that if the free energy of activation for a reaction is very high, it means that the reaction occurs very slowly in reality. But if the free energy of activation is very low, then it means that the reaction can happen very fast in practice. So people before us actually have calculate the free energy of activation for this process, and they find that the free energy of activation is actually very low, and it cannot explain the structure-dependent reactivity observed in the experiments. So when we start working on this, so we suspect that maybe the defluorination step is not the rate-limiting step for the whole reaction. Maybe the electron transfer step is. So in this way, we have to calculate the free energy of activation for the electron transfer step. To calculate the free energy of activation for this step, what we have to do is we have to construct a theoretical model for the hydrogen electron, and then we use a molecule theory. It's a calculation method to calculate the free energy of activation for this electron transfer step. So the conclusion over here is that the free energy of activation for the electron transfer step is much higher than the defluorination step. So it means that the electron transfer is rate-limiting. This is the mechanism we propose. And then we found that this mechanism applies to two molecules, P4A and P4S. We can see their electron transfer free energy of activation is much higher than the defluorination step. And also we calculate the free energy of activation for different chain lengths of PFCA, and we found that they don't change much among different perfluorocarbon chain lengths, and this is consistent with our experimental data. And for the PFSA, we found that the longer the chain length, the lower the free energy of activation, and it also consistent with our experimental observation that the longer the chain length, the higher the rate constants. So it verifies that electron transfer step is a rate-limiting step, and its theoretical calculation result is consistent with our experimental observation. So you may wonder why this structure does not have structure dependence, and this structure has chain length dependence. So the reason is because, so this is the electron distribution after the electron transfer. We can see that the electron prefers to stay with the carboxyl group, no matter the perfluorocarbon chain length. But for the this structure, the electron tends to stay with the perfluorocarbon chain. So in this structure, the longer the perfluorocarbon chain, the easier the electron transfer step. That means that in the reduction process, it will be easier to be degraded. So in this way, we can also identify the functional moieties that favor the electron transfer step, and their favorability can be ordered in this way. And using the same method, we compare the free energy of activation for the 41 PFAS we have investigated. We can see the free energy of activation is consistent with our experimental rate constant data. So again, it validates our proposed mechanism is correct. And then using the same method, we can identify which function moiety favors the electron transfer step. So the functional moieties on the top favors electron transfer, but the functional moieties on the below does not favor electron transfer. So it means that if a PFAS structure only contains the moieties in the below part, in the lower part, then it means that it cannot be very well degraded in a hydrogen electron-based system. And we also see the different degradation profile of this two representative PFAS. So for the P4A, we can see that their fluorine mass balance have a valley curve over here. But for PFOS, so this is a decay of parent compound, and this is a generation of fluoride. And we can see the fluorine mass balance is 100% over the degradation cost. It means that there is no detectable intermediates. But for P4A, there are a lot of detectable intermediates generated during this process. And these intermediates have low reactivity with hydrogen electron. That's why they can be accumulated and detected by the analytical instruments. And we have verified this hypothesis by experimental data, and again by theoretical calculation data, but due to the time limit, I'm not going to go details over here. And if you guys are interested in our work, you can always read our papers. So to summarize, so our study is working on the defluorination mechanism of different PFAS. And why this is important is because when we know the defluorination mechanism by a certain technology, we can understand the application scope of a certain technology. So for example, we can know that the oxidation technology can work on all the PFAS that contain these moieties. So in this way, if we know the contamination in the real industrial water, we can select the best technology to eliminate the PFAS contamination. And then by the defluorination mechanism, we can also understand the rate limiting step. So in this way, we can optimize and develop and improve the degradation efficiency. And also, we also by defluorination mechanism, we can also understand the structure dependence reactivity. So in this way, if we want to find a replacement for these structures, so remember that these structures are essential chemicals in a lot of industry process. And if we really want to use the structure, so what I'm trying to say is that we can use them wisely. It means that we can keep their functionality, but maybe the structures can be in low toxicity, low cost, and easy to be degraded. And our defluorination mechanism can certainly provide scientific basis for the easy degradability part. So that is the degradation mechanism and degradation technology study we did in the lab. But if this degradation technology can really be applied in the real industry water, so we have to do like pilot scale validation for different wastewater, and this is all in process in our lab. And also, I just want to summarize our current work. So our current work is what we have finished is the defluorination mechanism, how different structures of organic carbon-fluorine bonds was converted to fluoride ion and their structure-dependent reactivity. And the next step, what we want to do is to develop deployable technologies through pilot testing. And also another important work is that how to wisely use the fluoride, because fluoride is also a resource. We can consider them as a contaminant, but also we can also consider it as a very valuable resource. So how to recover this fluoride resource and convert them into high value products is also the focus of our next stage. So here is an introduction of our lab. So our lab is called Analysis and Degradation of Emerging Contaminants Lab. And we use mass spectrometry analysis and theoretical calculations to unravel the fundamental mechanism involving the defluorination of fluorochemicals. And we also develop materials and process for water treatment and cell remediation. And we also characterize the occurrence and environmental fate of emerging contaminants. So if you are interested in our work, you can scan this code, and this is our lab website, and you can know more information about our work, our recent work in our website. And that's all my presentation today, and thank you very much for your time and attending, and I'm willing to take any questions. Thank you very much.
Thank you, Yan Yan. So if anyone has any questions, please do tap in the Q&A and Q&A mainly. So I have just share this network QR code in case people missed my introduction to the network. So this is our QR code to join the BetterWater4All Network, and we'll have funding calls, working group calls, and workshop calls. So please subscribe. So thank you, Yan Yan, for the wonderful talk. I think one question for me is I think you also did some work in testing PFAS in wastewater, probably due to time limitation. It didn't introduce a lot of details for that work. Can you summarize that part of work?
Yeah, of course. So indeed, we also did a lot of testing work in environmental samples, actually not just about wastewater. We also did PFAS analysis in soil samples, in drinking water, and in quite different wastewater. For example, the municipal wastewater, the industry water from fluorochemicals, the industry wastewater from textile production, and also the wastewater that is affected by firefighting activities. So, and also from electroplating, from metal plating. Yeah. So the different industrial wastewater, they will have different characteristic PFAS. So first of all, their concentration are some of them concentration are very high, especially in the fluorochemical production site, and their concentration is very high, and their PFAS structures are really different. And also there are so many different PFAS structures. So for example, in the fluorochemical industry wastewater, we use target analysis and non-target analysis, and we have detected like 127 structures in the wastewater. So because that there are so many diverse structures in this industrial wastewater, that's why what I have shared today is that how different structural PFAS degrade. How can these different diverse PFAS structures degrade by different methods? It is because that in the wastewater, there are so many different structures of PFAS. And when we deal with the degradation of this PFAS in this wastewater, we cannot just deal with one structure or two structures. We have to find a general way, one technology, two technology, or combined technologies to degrade all the PFAS structures in this wastewater. So of course, I did a lot of testing work. So based on this testing work, I decided that we have to work on the differential mechanism of diverse PFAS structures.
Yeah, totally agree. So we know the fundamental mechanisms before designing any effective, innovative methods. But based on the measurements, especially in wastewater, do you see that the conventional wastewater treatment or the advanced oxidation in wastewater treatment facilities, did they have a good removal of PFAS?
So if we really want to remove PFAS from industry wastewater or drinking water, we can use sorption.
Yeah,
but
does not destroy.
Yeah, not destroyed by the sorption of activated carbon. But the problem with activated carbon is that they can only work on the long-chain PFAS. So the long-chain PFAS that has a carbon fluorine moiety that is over 6. And if the carbon fluorine moiety is less than 6, the activated carbon basically does not work at all. And another thing is that activated carbon is actually expensive for the water treatment company. So because recently I talked with them a lot, they said that unless there is a discharging standards, they cannot meet the standards of the discharging standard. They will use a very expensive activated carbon to stop the organic contaminants. Otherwise, they're not going to use this technology because it's very expensive. But yeah, if we really want to do a quick treatment, that is to use activated carbon, but activated carbon cannot work on PFAS that is less than the shorter chain version. And also, even though activated carbon can do a mass transfer to remove PFAS from the wastewater, but it does not destroy them. So eventually, we have to treat the soft PFAS very well. That means to destroy them.
Yeah, thank you. There's a question from the audience, Dr. E. Liu from LAFBO. She said, thank you for the nice talk. And it's a lot of mechanistic and informative controlled batch condition environment condition test. I wonder whether you are exploring in situ or continuous flow monitoring of PFAS degradation in more realistic water matrix, pH, dissolved organic matter, ions, flow conditions. You mentioned there will be like pilot scale study, but you have already some data on real water samples.
Yeah, we have actually we have some data on the effect of pH, the effect of non-organic matter, ions, but the flow condition not yet. We will going to do it in the pilot scale. Yeah, I didn't show this data because I want to show the mechanism, focus on the mechanism part. But for example, for the oxidation technology, we have to do it under low pH because under high pH, the radical does not work. So it has to be under low pH. And for the advanced oxide reduction process, it's actually in high pH. The pH is actually 12. And at lower pH, the protons will scavenge the hydrated electron. So of course, we have investigated the impact of pH, and also for how natural organic matter affects the oxidation process and reduction process. We also have that data, and for how common ions affect the reduction oxidation process, we also have that data. For example, chloride will scavenge the oxidation radicals, but it does not affect the reduction process. But over here, what I want to emphasize, not from another perspective, is that so if we are treating wastewater, we of course we have to consider the matrix effect, how this NOM, how these ions affect the degradation efficiency. But if we are treating the production wastewater, not the wastewater, but if it is the water from the production line, from the industry process, actually there is not much matrix in those water, and the PFAS concentrations in those water are highly concentrated, and there is not much matrix. And if we can degrade or destroy the PFAS at those places, and then we don't need to worry about they will contaminate our industry wastewater, municipal wastewater, or drinking water. So what I'm trying to propose is we don't deal with PFAS in the wastewater treatment plant or drinking water treatment plant, but we deal with the PFAS, we destroy the PFAS at the production stage, right after they use it, before they discharge into the wastewater. So this will save us a lot of energy and save us a lot of money. Yeah, so this is what I'm trying to propose. I'm talking to the water treatment company and the industry people. It's very hard, but they agree, but it's very hard to really apply and to do a pilot scale study because sometimes they are very conservative.
Yeah, I think that's really good point, and it also relates to the next two questions. One is that how scalable is your technology? What is the maximum scale you have performed experiments? So I think with your proposal, if it's treated at the industrial wastewater scale, then it can be scaled, right? Can be applied to a large wastewater treatment by the industrial production site.
Yeah, so if this is like, so what we really have is very small scale, like in the lab. And right now, like we are working on some like validation experiments to see how applicable it is. So for example, if we are doing a mechanism study, the concentration of PFAS we work on is only like 2 milligrams per liter. but I don't think this is a maximal concentration the oxidant can work on. So we are trying to increase the concentration of the PFAS. Right now, we have increased the concentration to 500 milligrams per liter, and under the same oxidant, under the same level of oxidant, the degradation efficiency is now reduced or now compromised. So this kind of validation is very important because for real production wastewater, the concentration of PFAS can vary. We want to know the limit of this technology. So this is a part we are currently doing. And also we are talking to the industry people and trying to set up a pilot scale study, a pilot scale non-instrumental treatment unit. And we will start with, like, for example, a few liters of water, and then maybe 1,000 liters of water, and try to scale it up, like one step by step. Yeah.
Okay, thank you. And next question by Tom Curtis, our project co-lead. How important is it for water companies to evaluate classes of PFAS in waters they are treating? I don't know what's the question. Tom, are you there?
I'm here. Sorry. Can you hear me?
Yeah.
Yeah.
It just struck me that you got a lot of insight by seeing which PFAS were removed and which weren't, but it's technically, I assume, quite difficult to do that. So if people start to introduce technologies, they could just look at the total amount of fluoride release, for example, and that would give you a crude measurement of treatment. But maybe we, at least initially, want to be more technically ambitious to find out what's being removed and what's not. So we may get insights into methods if we routinely do what you've done and classify look at the different classes that are affected. Yeah.
So look into the classes, you're saying.
Yeah.
You mean how to analyze the different PFAS classes in the wastewater?
No, yeah, but it's if people should, because it adds expense and complication.
So I think right now it's like people should analyze their PFAS classes in their water, in their wastewater. The reason is because so the industry people, when I talk to the industry people, what they are waiting is the regulation limits set up by the government. For example, if the English government saying like you cannot discharge PFAS or PFAS, so they will make treatment for PFAS and PFAS. But the thing is that if they deal with PFAS and PFAS, if they don't use PFAS or PFAS, they may use other structures, other similar structures. But if they're now regulated by the government, they will now treat them. So that's why, like in my study, I'm trying to emphasize is that there are diverse PFAS classes in those wastewater, and those structures can also induce a lot of toxic effect. Although, like in the near future, they will not be regulated because for the government, they cannot regulate everything, and sometimes they have enough data. They will only regulate one compound or two compounds, but that's not a sustainable way to solve the problem. So, like by academic people, like working in academic, is that we always have to do the right thing. The right thing is to analyze the diverse PFAS classes and try to find ways to degrade diverse classes, and then provide this information to the government and to the industry people. And like if the opportunity comes, we can really solve the problem. Yeah.
Good. Thank you.
Thank you. I think that's the end of our talk. Thank you, Yan, for the really wonderful talk. And thanks everyone in the audience that joined our first webinar. We will announce more webinars in the coming months. So please do subscribe to our network, and we'll have more interesting talks in the